Lecture AP 1.6, and this lecture is on acid and base stoichiometry. We're going to glimpse into acid and bases a little bit, and we're not going to stay very long, but we're going to apply our techniques of stoichiometry, mole ratios, to the basics of acid and base to show you where it implies, and we'll pick up acid and base more topics and in more detail, very much so, later in the year when it'll make more sense. In any case, we're going to just touch upon a few things and a few important facts that we need to have before we continue. I have the very basic definitions, and as was pointed out in class, this needs to be a base. Okay, hopefully Jesse is paying attention. So this is, of course, a base definition. Okay, and as I was talking about in class, three basic definitions are Arrhenius, Bronsted-Lowry, and Lewis acid. Arrhenius, okay, was the smallest scope or definition that was smallest in its scope, and he just said to be an acid, you are responsible for the protons in solution, so you have to have a proton built into your compound. So hydrochloric acid, of course, is an acid because it gives off a proton, okay, and of course chloride ions, but that's what it does. So it has to have, like, so hydroiodic acid, same idea. Okay, you see that H given off. So generally speaking, Arrhenius acids are those that have the proton already built in the formula to show that it gives that off. Arrhenius base, by comparable ways, has to have a hydroxide ion built into the compound, like so sodium hydroxide is an Arrhenius acid, a base, I'm sorry, because it gives off a hydroxide ion. Okay, so anything with a hydroxide ion, and of course it has to be an ion, of course, not bonded OH. Hydroxyl group is an organic compound like an alcohol. So this, of course, is an alcohol we talked about. Okay, C2H3, C2, I should say H6O. This is an alcohol, ethanol. But in any case, those are the easiest definitions there. Bronsted-Lowry expanded the definition to include some compounds that didn't have an H or an OH in the compound, yet were still acting as a Bronsted-Lowry an acid or base because they were donating or accepting protons. So obviously these acids were acids because they were donating a proton. Sometimes you don't make free protons. Protons are too reactive, as I said in class today. Think about a point charge proton. It's +1 over a small area. Those things are way too reactive to stay that way. They're going to mess around with electrons and bonds. Okay, and like I said, it's a heat-sinking missile for electrons, so they're not going to stay around, really. In fact, what Bronsted-Lowry introduced was the idea of something called the hydronium ion. And I don't know if he specifically or this pair of people who worked on this definition did, but if you think with me, this reaction has nothing to do with this above here. But so let's say you have hydrochloric acid in solution. Well, you have a lot more water than hydrochloric acid. What's going to happen is, of course, the acid's going to donate the proton to the water, and you're going to make this hydronium ion, which you learned in Regents chemistry is synonymous with a proton, but it's a water holding on to a proton, and then of course you have the conjugate base. Remember that word conjugate is what's left over after the acid donates. Here's the conjugate acid, here's its conjugate base. All right, so it really, you don't have free protons in solution, and that's what's so simple about these definitions. Nor do you have free hydroxides. You probably have some, but very, very small in quantity. These compounds right here are just too, or ions are just too reactive to stay floating in a solution. So in truth, a better definition for an acid is donating it. So truthfully, if you have hydrochloric acid in solution, you have a bunch of hydronium ions. I mean, measure this through pH. Okay, if you remember, pH was the concentration of the proton, or better yet, the hydronium ion. So if you had a concentration of 1 × 10⁷, okay, that would give you a pH, if you remember, of 7. And we'll do more of that later in the year. I'm not really into that right now. Okay, we're talking about stoichiometry. Okay, so just giving you some basics that we'll talk about. And of course, a Bronsted-Lowry base, okay, for instance, if you have something like ammonia, okay, as I talked about in class, that loves in contact with water. It produces a hydroxide, which will go on and react with other things, but indirectly it accepts a proton. Okay, as I talked about in class, it's got that lone pair that drives its chemistry. Okay, So very basic organic compounds have nitrogen in them, and of course this accepts that lone pair and becomes NH4 plus, the ammonium ion. Hey, that's one of the ions that we used in our lab. And you have that, okay, and that's how that goes. And of course this is the conjugate base, this is its conjugate acid, and this is a conjugate acid base pair, if you remember. Okay, it's the same chemical plus or minus an H, and we'll talk more about that, but those are the basics you'll be hearing about. Okay, what is this Lewis acid and base about? Well, there was an even better definition that was describing compounds that weren't donating H's and donating and accepting protons, or donating protons. And if I can just get my eraser here to work, yeah. And the case in point I gave you in class was CO2. CO2, interesting enough, because it's a very electronegative atom, on the end was pulling the electrons away from the carbon, exposing positives. So this carbon actually was very, very susceptible, because of the structure of the very electronegative oxygens, to accept a pair of electrons from water. So by accepting a pair of electrons from water, it was acting as an acid. It's an electron pair acceptor. Now the way that is very easy to remember, the most simplest form of an acid is a proton, right? And what does it do? It accepts a pair of electrons. You may say, well, why? Well, remember, it has 2 electrons in its energy level, 1s2. So it wants to fill its orbital, its s orbital, to be stable. Besides, it's small and +1. It needs stability, and this small +1 gives it the avenue to really become stable. So very, very reactive particle that is given off by acids. And of course, as I talked about, the reason why they're so corrosive is because of its ability to draw electrons in. It's a strong oxidizing agent. It forces the loss of electrons from bonds and so forth. And we'll talk more about that as well. In any case, what is another great example? Well, back to the CO2 example. The CO2 example I was talking about in class. What would happen is this carbon dioxide, okay, this thing would, let me just change my inks here. This water would come and attack this, or be attracted to this carbon, or this carbon would draw the electrons in, it would push this pair out. And what would I have, and just erase what I made here, as I was trying to draw on the way out today, carbon would make a -1 here, this double bond would stay, and we'd have this carbon bonding to this, and this is a positive, and this oxygen would migrate over here, and what you have is the bicarbonate ion, which is H2CO3, which is very unstable, okay, and which will break down into CO2 in water. And that's what you saw in one of your reactions. That's an acid-base reaction that you had in your lab. Okay, you made carbonic acid, which means you had a carbonate ion, CO3 -2, and it accepted H's. Okay, accepting H's is the Bronsted-Lowry definition of a base. Okay, that's why carbonate ions are very strong, very good bases. Sodium carbonate is called washing soda, and a strong base is a good caustic kind of a compound that will also wear away at things. Okay, so you can see though what I'm trying to get at is that water gave its electron pairs to the carbonate ion, and in fact, okay, made the pH drop. Okay, now why? Because it made something called carbonic acid. Now carbonic acid, if it breaks apart into CO2 and water, it won't drop the pH, but this can give off an H+. And left over HCO3-, which is a bicarbonate ion. Okay, so indirectly, by accepting a pair of electrons, the CO2 produces protons, which drop the pH. Another example we'll get into, okay, is the cations of some small metals. For instance, if you look at copper, copper is +2, and it's a pretty small +2, so it's got a pretty high charge density. And it actually attracts a certain number of water molecules. And these water molecules surround this ion, and the attraction is so great, the coulombic attraction is so great here, this ion actually attracts the electrons in these bonds, and I'll draw one here with the bonds between the O, and draws them in closer. So it's called electron drift that pulls on these electrons in these bonds here to go closer, which means you have these hydrogens who are electron deficient who can slough off and become H+. So their electrons are kind of pulled in by this positive ion. So if you have copper ions, as I'll show you tomorrow, or other kind of ions, they can make a solution pretty acidic, okay? And of course, copper doesn't have any H's. No H's to give, no H's to donate. So how does it make the pH drop? It does so by accepting a pair of electrons from the oxygen, and therefore acts as a Lewis acid, okay? Now I'm going to get into where the stoichiometry comes into play, and it's very important that this background is understood.